Yeah, thank you very much. Originally, I was scheduled to give a talk before John, but now that we swapped, he he provided a really great context about why we're so obsessed with cables of figure eight and why slice ribbons is an important question. Hopefully, now you'll understand we're not just random weirdos obsessed with figure eight. Yeah, it has some reason. Okay, so yeah, yesterday we talked about the non-sliceness of 2-1 cable of the figure eight smoothly. So like why it's not sliced, how do you prove it using Heger involved in Heger flow homology together with the deck transformation, and why it's actually infinite order, and how can we generalize this figure eight into other knots? Like Miyazaki's family was about not just figure eight, it was about all negative amphichiral, not which is fibered and with irreducible ascendant polynomial. So yeah, we generalize this like to thin knots with non-zero R invariant, or if we just need slight non-sliceness, then yeah, half of the all negative amphichiral knots. So yeah, that was yesterday's story. And today's story is that we will try to diverge from this setting of 2-1 cable to 2n, 1 cable when n is not, because Miyazaki's story applies to all parameter n, not just 2, 1. And the disclaimer is that the price we pay is that we will not even try to switch for one to other NOS, because currently we are not able to do that. And we will also not discuss about having infinite concordance order, because currently we don't know how to prove that either. But I'll tell you that at least when for like 2n, 1 and when n is odd, so 4n plus 2, 1, then at least we will get the non-slices done. And of course, the first question is how do you prove it? Because it's a very non-trivial question. And well, I gave you how to prove the non-sliceness in the 2, 1 case, the n equals 1 case. So why don't we try to reuse the same argument again? I think yesterday I tried to explain why this is not gonna work. The problem was that the most central topological observation in the proof relied on this Montesino trick. The 2, 1, cable of any knot K, if it's just K, then its branch double cover is identified with K connects on K reverse, and you take +1 surgery. And it works with any knot. And the deck transformation here is identified with the induced symmetry here given by the natural strong inversion of K and K reverse rotating each other. And if you from here, you can see that it really depends on the natural Mobius strip bounded by the 2, 1 pattern. If we switch to 2n, 1, then it doesn't bound nice surface anymore. So this kind of argument cannot be used. We don't even know what does the branch double cover look like topologically. So so the first question is, what should we do in this case? And here comes the first into the solution. So after we published our 2, 1 proof that the non-sliceness of 4 and 2, 1, the year after that, John Park, together with various other people, found a much easier way to prove this non-sliceness, where you lose the flexibility about your knot. You cannot deal with any negative thin knots with R invariant 1, you cannot do that anymore. But if you are you only want to prove that 2, 1 cable of the figure 8 knot is not sliced, there is a very much easier way, and it uses this magical concordance. And this is a smoothly embedded cylinder, but it's not embedded in S3 cross I. This is a surface in C2, twice punctured 2 CP2. And how you see this is that here's a figure 8 knot, and you have to take a satellite, so you have to care about the framing. Let's say it's cipher frame. Then you isotope like this. It's kind of magical picture, isn't it? And here you add -1 full twist here and here, which is equivalent to saying that you're blowing up here and there. And then the ambient space is S3 with blown up twice. No. It's +1 surgery, so it's not blown up. It's 2 CP2. But anyway, so the ambient space becomes CP2, but then you get a full twist added here and here, and magically it unknots the figure 8 knot into the unknot. But here, the framing gets changed because, here you're twisting, and twisting changed the framing. It becomes -10. So what did they find? Find is that there is a smooth concordance from figure 8 to the unknot inside the twice punctured CP2 with homology class 1,3, and the framing goes from ciphered frame to -10. Then you take the 2,1 cable out of the concordance. And here's where this framing comes into play. Here, when you take a satellite, it just becomes a 2-1 cable, but then the framing induced by this concordance is -10 relative to the ciphered framing. So it becomes 2, -12, 20 plus 1, which is 2, -19. So what you get is you get a smooth cylinder in the same ambient space with homology class doubled, so 2,6 from 2,1 cable of figure 8 to torus knot T2 -19. But now there's the Miller conjecture, which is proven to be true for torus knots. So what is this? The slice genus of this thing is the same as the cipher genus, which is for TPQ is P minus 1 Q minus 1 over 2. If you compute it, it becomes genus 9. So it bounds a smooth genus 9 minimal genus surface inside the 4-ball. So if we consider this construction, where you divide the S4 into oh, sorry. You divide CP2 into 3 parts. This is not S3 cross I. This is 2 CP2, sorry. So here you attach your cable concordance. Here you assume that on the contrary that this is slice and attach your hypothetical slice disk here. And here you attach a cipher surface here. It becomes a smooth surface of genus 9 inside 2 CP2 of class 2,6. But it's already known from pin-to equivalent cyberwritten theory that the minimal genus for smooth functions, smooth surfaces of this homology class is actually 10. If you assume that this exists, then it will be 9. So contradiction. So it's a much easier proof where we have to sacrifice the flexibility about your knot. Okay, so this is a starting point for our argument. So here, to construct this, we cabled our concordance from figure 8 to the unknot. You just apply the 2,1 pattern. What if we just apply 2n,1 pattern and try to apply the same strategy? You assume that this is slice, you attach your hypothetical disk, and it will be some torus knot. So you attach the minimal genus, which is just a cipher surface, and try to derive a contradiction from the minimal genus of the fixed homology class. Turns out that it doesn't work because your genus, we don't know much about the genus functions, and the upper bound is too big. But still, we can do something. Instead of capping off your surfaces, so let's just not cap off here and just assume that this is slice and cap off with this hypothetical disk here. So we will not get a closed surface. Instead, we'll get a once punctured 2 CP2 with the homology class 2n,6n, where the right boundary is given by the torus knot 2n, 1 minus 20n. Oh, what's happening? Sorry. Okay, so that's our concordance CN. So what's gonna happen if we use this? We'll have to use some gauge theoretic invariance to obstruct the existence of such a concordance. But hopefully it'll be very, very computable because branch double cover of torus knots are rational Briscoe spheres. And usually gauge theoretic invariants are only computable for ciphered fiber things. So it's a bit hopeful. But just cyberwritten theory will not work because we have to. So if you recall what kind of data we used in the yesterday's talk, we used iota and we used tau. Iota means we're using spin structure. Tau means we're using a deck transformation. So we have to somehow use both. There are some theories that use both. The pin2 symmetry and the deck transformation Z4 symmetry can be merged to give a big total symmetry group, but it's too big. There's a nice way to do this, developed by Hokuto Kono and Masaki Taniguchi and Jin Miyazawa. It's called the real cyber theory, and that's the tool that we're going to use to compute everything. Okay, so we start with a spatial refinement of the easiest case, the S1 equivalent cyber cohomology, which corresponds to HF minus due to works of a lot of authors. I don't remember any of them, sorry. But anyway, this spatial refinement, or like cyber spectrum, is defined by Bauer and Furuda. And for simplicity, we stick to compact connected oriented rational homology spheres. We don't want to deal with the B1 non-trivial B1 cases. So let's let Y be such a very, very nice manifold. Then the spatial refinement says we have a finite S1 spectrum, SW, which we'll call SW of Y. It's usually called SWF, but I'm going to use SWF for cohomology. So, and here the S1 equivalence is a S1 spectrum, so you can compute the S1 equivalence table homotopy type, and it can be defined so that homotopy type depends only on the diffeomorphism type of Y. So it's a well-defined topological invariant. And it is indeed a spatial refinement in the following sense. So a priori, we had just SWF, which is just cohomology theory. What the spatial refinement says is that the spectrum invariant you defined computes your cohomology in the following sense. The S1 equivalent cohomology, there is a canonical isomorphism between this cohomology and SWF. And furthermore, we have a natural splitting into spin C structures, as in the Heeger-Floor sense. Everything is very expected. And this isomorphism will also split along the spin C structures. And this is a very basic case. And S1 doesn't have any iota symmetry or tau symmetry. The first thing we'll discuss is what corresponds to the iota. It's very well known. It's the element J, is a quaternion in pin2. So it's called, in this context of cyberwritten theory, it's called this charge conjugation symmetry, which is a symmetry of the cyberwritten equations which arise when you deal with spin structures. And in which case S1 and J generate the group pin2. Yeah. It was actually the one used by Manolescu in this proof of the triangulation conjecture in all dimensions. Okay, and we now have to incorporate the tau symmetry, which requires that we have a odd action. So our setting is that we have your three manifold with a branched up cover of S3 along a knot, in which it carries an involution tau, which conjugates all the spin C structures. And it then induces an action on the cyberwritten spectrum. And as it's a bit unexpected here, but since it's an odd action, so it conjugates all spin C structure, it turns out that this is not, the action on cyberwritten floor's spectrum is not order 2. It is order 4. And it has the relation that it squares not to identity, but rather to -1. -1 is the antipode 1 inside the identity component of pin2. Okay, and then the total symmetry group that you get by merging S1 and J and tau is given by this group, whereas pin2 cross Z4 modulo tau squared equals -1, so J and tau commutes. Then SWF, the spectrum itself is defined by this procedure called the finite dimensional approximation. It can be done in a very equivariant way, so you can endowed with a natural structure with a finite G spectrum. And ideally, it'll be really nice if we can directly compute this stable G equivalent homotopy type. so that we know maximum amount of information we can achieve. And of course, it's impossible. It's currently not so possible. It's too hard, even for this ciphered fiber cases. So we will have to truncate some information in some way, and that's precisely what real cyberwritten theory does. Instead of trying to deal with the whole great giant symmetry group G, we uses the fact that tau is order 4. So if you consider J composed with tau, which makes sense because they commute, then what is I square? I square is J tau, but they commute, so it's J square tau square, so it's minus 1 squared to 1. So it's an involution. And it fixes all spin C structures because J and tau reverses everything. Which means that for every spin C structure, the I action will act on each component, the SWF of sigma k comma s. Then we consider the geometric fixed point spectrum for this action. So we take the geometric fixed point spectrum, declare that this is something called a real cyberwritten homotopy type. Not precisely, because in order to call this a real cyberwritten homotopy type, we have to endow it with a Moore action, which comes from J. So J acts on the whole thing, but it commutes with I, so they're commuting things, so J action will restrict to an action on this fixed point spectrum. Of course, when you're working with a spin structure. That gives this one a natural structure of a finite Z4 spectrum. J is also order 4, so. And we're working over the universe R infinity plus C infinity, where the S1 action on R infinity is trivial and C infinity is complex multiplication. This spectrum together with the Z4 action is called the real cyberwritten spectrum. But however, instead of computing this homotopy type, it's still too hard. So we'll only consider its mod 2 coefficient Z4 equivalent cohomology is a rationally graded module over this ring. Oh, sorry, it's Q square. It satisfies very similar things expected from the Higgs floor side. First thing is that it satisfies the localization formula. So formally inverting U gives standard stuff free of rank 1. Which means that by looking at degrees of its U towers supported on U1 or Q, it can be used. And if you look at the maximal grading, that can be declared as numerical invariance, which we call delta R upper bar and delta R under bar. We call them real Furshov invariants. They're rational numbers. It was defined in a paper of Kono, Miyazawa, and Taniguchi. Okay, so they're nice, well-defined invariants, but we need more than that because we're approximating our 2n-1 cable by a very, very nice knot by a cobordism. So we need some kind of cobordism inequalities, which comes from cyberwritten cobordism maps. If you have a cobordism, well, due to the fact that cyberwritten equations are actually 4-dimensional geometric equations, you can define cobordism maps given a 4-dimensional cobordism between 3 manifolds. So more precisely, so if you have a smooth equivariant cobordism, equivariant means that tau has to be strictly order 2 diffeomorphism and a codimension 2 fixed point locus, which is very different than what happened in the Higgs floor mainly because it has much more information. So anyways, if you have a smooth equivariant cobordism with a real spin C structure, real means that the tau pullback S is conjugate of S. We call it a real spin C structure. Anyway, so if you have this kind of cobordism between sigma k and sigma k prime with B1 equals 0, then you can define a homotopy class of a map, which is well defined, between the real cyberwritten floor spectrum. And given that, we would like to obtain an inequality between real Furshov invariants. In order to do that, the only thing you need is to compute this localized map and see where it has to be non-trivial in order to have some non-trivial inequality. And to do this, we consider the action of tau on the second R coefficient cohomology of your cohort, together with the intersection pairing. So if we will first look at the maximum dimension of positive definite subspaces. We say that it's B plus. Well, if you know four-dimensional topology, it's just B2 plus. And B fixed plus is the maximum dimension of tau fixed subspace of positive definite subspaces. If they are equal, then this is a condition where this is guaranteed to be an isomorphism. Well, probably I should say homotopy equivalence. But anyway, so under this setting, we will have these kind of two inequalities. So degree shift is some kind of homological number involving like C1 square and signature Euler characteristic, blah, blah, blah. Yeah. But yeah, this is a well-defined rational number. And with this shift, we'll have an inequality between the real Fauchev invariants on both sides, which implicitly implies that they are concordance invariants, because if your W is a branch double cover of S3 cross I along a smoothly embedded cylinder, then degree shift will be zero, and it works on both sides. So we'll have an inequality. That's why they're concordance invariants. On the other hand, if they differ by one, so if B plus is B fixed plus 1, then it's not homotopic equivalence anymore, but it's equivalent homotopic to Q times identity. In this case, we'll have this, because one tower, the tower here will be mapped to the tower here. And we'll still have this degree shift term. And the notable case is when this is when you have a W is defined by taking branch double cover of a smooth coborsum between embedded in some four manifold. Twice punctured four manifold X. In this case, you can compute the degree shift in terms of self-intersections and signatures of the boundary and signatures of your four manifold. Precise formula is this. It's 1/16 times -2 signature plus half self-intersection plus difference between signature of boundaries. And furthermore, this condition also has to be computed. And in this case, it's computed as follows. There's B plus of X plus 1/2 B1 minus 1/4 self-intersection minus 1/2 of the signature difference. Okay, let's go back to our concordance, which is the only thing that matters, of homology class 2n, 6n in CP2 from 2n, 1 to this very, very big torus knot. And we're dealing with n is odd. And this condition is really important, because if n is odd, then this homology class is divisible by 2, but is not divisible by 4. And this condition is that assures you that the branch double cover always admits a real spin structure. Now we have to apply this formula, and that gives you B plus minus B fixed plus is 1. So we're very nice. So we have to now apply this inequality. And in order to do that, we have to compute the degree shift. It happens to be -1/4. No, 1/8, sorry. So if this were smoothly sliced, then we would have -1/8, like less than or equal to delta real upper bar real Fauchev invariant of torus knot 2n, 1 minus 20n. Our goal is to show that this is false. Actually, we'll show that this is -9/4, 9/8. Okay, so how do we do that? That's a completely different question, because we have to now explicitly compute everything. There's not much techniques known in this direction. It's relatively very new. But anyway, this is defined in terms of real cyberwritten homotopy type. And real cyberwritten homotopy type is defined in terms of I action on the cyberwritten homotopy type. So somehow we have to study the cyberwritten homotopy type together with the I action in order to compute anything. And the last year fall, Dai and Sasahira and Stoffregen wrote a paper which was the first known way to compute the cyberwritten homotopy type for ciphered manifolds. It's called the lattice homotopy type. I'm not going to explain the machinery of lattice homology. It's a lot of detail. Roughly speaking, what it's going to do is that you try to understand the gauge theory of a very nice Plum manifold in terms of the Plum 4 manifold bounding it and all possible spin-C structures inside it. And the Plum, in order to do that, the spin-C structures should contain maximal possible information about the boundary. And that condition translates to plumbing graph being almost rational and negative definite. And well, negative definite means negative definite. Its intersection form is negative definite. It is guaranteed when all coefficients are at most -2. And almost rational means that it has at most one bad vertex. Bad vertex means that its multiplicity of any node is bigger than minus the valence of that node. So, and the only thing that is relevant in this talk is our case. The sigma 2n minus 20n minus 1. By computing the three singular fibers for the ciphered S1 action, you can draw the plumbing graph explicitly in a symmetric way. So it has three singular fibers. One is just -n, and the other one is these things, and they are swapped by the back transformation. And here, this is the only bad vertex. So the technique of so you can apply lattice homotopy type. Okay, and now the next step of the computation is to draw something called the graded root. It comes from the ancient work in 2003 due to Andras Nemeth. It is not an easy computation, but it can certainly be done by a computer, but somehow we will not compute it in any way. Because we're not going to draw graded root. The only thing that matters is that it exists. So instead of trying to draw graded root from this horrible plumbing graph, we'll just pretend that our case is very simple. We'll pretend that our case is sigma 237. It is very wrong because, first of all, this has H1 equals C2. This is a homology sphere. Yeah, it's a bad comparison, but it doesn't really matter. We only have to know that graded root exists and how they work. But anyway, how they are shaped is a infinite tree together with the grading. And each level are differ by grading too. So for 237, it's shaped like this degenerate fork or something. From here, we can immediately read out the mod 2 coefficient S1 equivalent cyber-written cohomology. So how you read it is that you have this free tower, and here this is order 1 torsion. But that's not the one we need. We need to compute the homotopy type. So the strategy of Dai, Sasahira, and Stoffregen is first to build a cell lattice homotopy type from this graded root. Well, actually from the plumbing graph directly, but it's kind of the same. And then they construct a S1 equivalent homotopy equivalence from here to the cyber-written homotopy type. But anyway, we have to understand this first. And how do you construct this from a graded root like this is that each leaf of degree, let's say d, some even number, corresponds to complex and 1-point compactification of complex vector space of dimension d over 2. And here S1x by complex multiplication. And here for each angle means this kind of thing here. If this is, for example, if this is degree 0, and then this is the angle of degree -2. Given such an angle between two leaves, let's say v and v prime, of degree dv and dv prime, we identify the corresponding leaf spaces by gluing them along their linear subspaces of the dimension d mod d over 2. You might ask, well, what if dimension is negative? Well, we're actually dealing with a spectrum, so they're formal d suspensions. Okay, so let's, as an exercise, let's try to draw some suspension of this lattice homotopy type of this 237. This lies in 0 and this lies in -2. Let's shift the grading so that this is 2 and this is 0. So you have 2 leaves in degree 2, 1 leaf in degree 0 between the 2 leaves of degree 2. So for each leaf, you have one-dimensional vector space here, and there. And they have to be compactified, so they become spheres. And S1x by rotation. Now, the angle here has degree 0, so they have to be joined along the C0 plus, which is 2 points. So it's a banana. A very simple banana. Yeah, I want to eat them, but anyway. Okay, so yeah, that's very roughly how things work. So in the S1 equivalent case, they show that there's a natural map defined in a very similar way as how Nemeth proved that Seibertin homology or Heeger-Floor homology is isomorphic to lattice homology. It's defined by joining a bunch of coordinate maps given by various Pincy structures on your Plum 4 manifold. And then they prove that it is a homotopy equivalence by looking at this fixed point subspaces of the normal subgroups and proving that they induce isomorphism in homology. Okay, so and thus we can compute this table homotopy type of Seibertin spectrum in this case, which we're not going to do. But important thing is that we can also identify the I action, ISJ tau. It is the reflection followed by complex conjugation. And well, reflection comes from the fact that tau reflects two things, and J is complex conjugation. So we see that the I invariant locus. So for example, if it's this, then the I will act by exchanging these two bananas and rotating by 180 degrees. No, actually, sorry, reflection by this plane. Followed by the swapping. In which case, the fixed point locus will be just the thing on the middle, but then it should be half dimensional because it will be acted upon by complex conjugation. So you only count the real dimension. Okay. So that reduces the degree of the space by half. So in any way, the nice thing is that the I invariant locus should be sphere in any case. It doesn't matter how complicated your graded root is, it's always going to be a sphere. And this degree is actually given by the Neumann-Sieben-Mann invariant. It can be computed directly from our plumbing graph. It turns out that in our case, it's 9/4. Well, you might ask, well, why is your dimension rational? It's formal. It's formal thing. You formally shift things by irrational things. Okay, for this, it might be tempting that we can now conclude that this real Seibertin theory spectrum is spherical. And if this is indeed true, then what will happen? Then we can immediately deduce that the delta upper bar and lower bar is just the 1/2 of the Neumann-Sieben-Mann invariant, which will be 9/4, 9/8, since the spectral sequence will collapse. But however, unfortunately, we cannot say this right now because we are unable to show the existence of an I equivalent homotopy equivalence. It is a homotopy equivalence. We don't know, and it's also an I equivalent map. We don't know whether it's an equivalent homotopy equivalence. They're different things. But anyway, as I said, we have an existence of a homotopy equivalence, which is also an I equivalent map. And now I generates a Z2 group. It's an involution, and so it's a finite 2 group. And this domain and codomain are finite Z2 spectra. So now we can invoke Sullivan conjecture to show that it induces isomorphisms between the mod 2 cohomology of the fixed point set. And we know that this is a sphere. So we also know that this is mod 2 homologically a sphere. And that's enough to use this argument, spectral sequence argument, to declare it. So everything looks acts very spherically, and therefore this will be deduced. Yeah, so we finally arrived at the conclusion that they are both 9/4. Well, and it's 20 minus 1, so we have to invert it. So it becomes minus 9/4, 9/8. But recall that we had this inequality. So if this is smoothly sliced for some odd n, then we will have minus 1/8 less than equal to this thing. But now this is 9 minus 9/8. So it's violated. Therefore, we deduce that this is not smoothly sliced. Okay, so then actually we can say a little bit more than just non-sliceness. So we just apply the same strategy. Yes, we can prove that this does not bound a normally immersed disk. Normally immersed means that it's immersed, but the only singularity types it can have is double points, transverse double points. And what it doesn't have is a normally immersed disk with only negative double points. Double point can be positive or negative. It cannot have just negative things. And to see why, if you for each negative double point, the local model is a negative half link. If you take the +1 surgery here, then it'll be unlinked. What does it mean is that if your disk has only n negative double points, then you can do this on every double point to show that it bounds a smoothly embedded disk of homology class 22222 in NCP2. Then we can apply the same cobordism inequality, which gives you that your underbar real Forshev invariant is non-negative. Which will, so we had this inequality between this 4(1), 2n1, and the force knot. So composing that, we see that this same inequality should be satisfied again, which we know is false. And so it's contradiction, so we prove that it doesn't bound a normally immersed disk with only negative double points. It also means that you cannot unknot this thing by resolving, by only negative crossing changes. Because if you have each negative crossing change will create a negative double point. Okay, so this is a rough sketch of the proof. I think it was probably not so rough, but anyway. So we have some remarks here. So can we prove that it actually has infinite order in the concordance group? I think it will involve some K theory, some equivalent K theory here. And we can also ask whether it bounds a normally immersed disk with only positive double points. So it's a bit technical. It's a bit tricky because 4(1) itself is amphichiral, but once you take a cabling, and now it has some kind of positivity here. Its mirror image will be same knot, but 2n(-1) cable. They're different things. And we can also ask, what about other negative amphichiral knots? So can we do something other than 4(1)? Actually, we can, because there's very restricted infinite family, where you can draw the similar metrical concordance. Yeah, but it's a very restricted setting. So we can ask about, can you do a more general constructions? And also, clearly, our argument fails when your parameter n is even. And that was because the branch double cover will no longer have a real spin C structure. So we can ask how to deal with that case. Probably branch cyclic cover or force cover. I don't know. You can try. And furthermore, probably slice ribbon conjectures might be true, isn't it? Yeah, I don't know whether you really believe it or believe it to be false, but but honestly, I don't know. Probably it'll not be very surprising if it turns out to be true. So yeah, how do you think? Thank you so much.